Hello, moving on to video 5.1. So we're moving on to chapter 5 here. And so just sort of a recap where we're at. We've spent chapter 1 learning about sort of the mathematical formalisms for making measurements and reporting measurements, significant figures, error, accuracy, precision, etc. 2, we moved on to sort of the subatomic makeup of an atom and how the number of protons dictate what the element is and its chemical properties. The number of neutrons dictate its sort of ultimate mass and whether it's an isotope. But we haven't really talked about the electrons very much. We said that they're about 10,000 times lighter than a proton and a neutron, but we didn't really talk about how the electronic structure, the electrons within the atom, how those can be sort of inferred from the structure of the periodic table. So we're going to start by just thinking about this notion of periodicity. And periodicity is specifically related to the periodic table. So periodicity is thinking about how trends manifest inside of this table. And we've talked a little bit about some of them already, just thinking about like oxidation states and how those differ across the table and how we can think about these as +1, +2, 0, -1, -2, -3, etc. But we haven't talked about things like the size of an atom, the size of an ion, the reactivity of certain things, all of which are dependent upon the electronic structure. So how those electrons are organized in those specific atoms, and the periodic table can tell us a lot about that, that organization. So I'm going to start by just showing you a periodic trend, and then we'll discuss a little bit later exactly the origin of it. And so if we look at the figure over here on the left to start with, what we're plotting is the atomic radius. So the atomic radius is, you've got an atom and you've got the nucleus in the center. The radius is going to be this width here. So this radius in picometers, so really small, for all the different elements on the periodic table. And this is plotted as a function of atomic number. Remember, atomic number is the same as Z, which is the number of protons in the particular element. And that's that number right at the top in the symbology of the periodic table. So for hydrogen, you've got 1 proton, lithium, you've got 3, etc. Okay, so you've got this sort of weird structure in this plot of atomic radius versus the number of protons. So if we start at hydrogen, what we can see is hydrogen is really tiny, as it should be. It doesn't even have a neutron. It's just a proton and an electron. And if we go from hydrogen to, in this case, lithium here, the one in pink, we get a pretty significant bump in the size of the radius, and that should make sense, right? We're packing in more stuff into the center of the nucleus. What's interesting, though, is that trend doesn't just continue, right? Otherwise, we'd expect that as the atomic number went up, we'd just get consistently larger and larger and larger atomic radii. But instead, what we see is we see the big jump to lithium as we move down one row, but then as we move across the row from lithium to beryllium, so from 3 protons to 4 protons, we actually see a decrease in the atomic radius, and that continues as we go from beryllium and continue all the way across the table to fluorine in this case. And so fluorine, even though it's in the same row and it's got 6 more protons and 6 more neutrons than does lithium and a whole bunch more electrons, it's actually considerably smaller, way smaller than its counterpart of lithium. But then once we jump down another row, we get to see the same big jump from fluorine back up to sodium. So when we jump rows, we see this sort of stark change. So going from fluorine, we go all the way down to sodium, get a big jump, and then we start to see a small decrease as we move across the row again. And we can see this cycle occurring every time we decrease down the row. we make these big jumps, and the size, the atomic radius goes up quite a bit, and as we move across the rows, then it slightly decreases. And so we need to think about, you know, what's causing this? What about the electrons in their organization around the nucleus gives rise to this simple difference in atomic radius, or this fact that it's not really monotonic. It's this sort of staccato rhythm. So to understand periodicity, we need to understand the electron organization in the atoms. We need to understand the energy of those electrons in the atom, and ultimately we need to understand how do we probe this experimentally. And so traditionally the way that we learned about and still learn about electronic structure is through this technique called spectroscopy. So spectroscopy is the study of the interaction between light and matter. And it turns out to be one of the most, if not the most, useful techniques in all of chemistry and physics. So essentially we've got some matter, and we're going to shine light on it, and we are going to have some interaction between the light and matter, and that may result in a change in the energy of the light, or the change in direction of the light, or some sort of change that we can measure, and that's going to tell us something about the electronic structure of the material that we started with. So we're going to dive in a little bit to electron spectroscopy and the electromagnetic spectrum before we get back to answering these questions of well, why do we actually observe this trend in the periodic table? So all of light is composed of these particles that are interesting because they behave both like a particle and a wave. So a light can be thought of either as sort of this point particle or as a wave. We'll talk a little bit about that, but we call these things photons. And photons are organized by their wavelength. So we think about them in their organization in terms of this sort of sinusoidal wave. And wavelength is the distance between two peaks or two troughs in that sine wave. And we often denote that as the Greek letter lowercase lambda. So that's the wavelength. And so all of light is organized or categorized based on the respective wavelength of these photons, and we call this the electromagnetic spectrum, or the EM spectrum. And I'm showing you a version that comes from your textbook. And so what we see are a variety of different classifications of photons by their wavelength. So we have wavelength in meters here. So this scale, this is wavelength, lambda, in meters. This is getting smaller in this direction. So really, really small wavelengths. And then this is getting larger in this direction. So wavelength goes up if we go in this direction. So the waves of photons in this case can be broken down into the sort of general regions that we're used to. So we'll start there. So humans, we've got built-in sensors in our eyes that can sense or measure only a certain portion of this electromagnetic spectrum, and that's what we see as color. So this very narrow band that is right between ultraviolet and infrared. It's really, really narrow respective to the rest of the size of the EM spectrum. But we've got these special tools in the back of our retina called cones, and they're proteins that change shape depending on the wavelength of light that strikes them. And we actually have 3 different cones that is sensitive to red, green, and blue light. And because all light can sort of be derived from red, green, and blue, we can sense a fairly good spectrum of colors between violet and red, and we call this the sort of spectrum of color, which we all learned when we were in probably middle school as Roy G. Biv. Standing for red, orange, yellow, green, blue, indigo, violet. And so actually this is inverted to the color wheel here, where you have violet out here, indigo, blue, green, yellow, orange, and red out here. Okay, so this is what we can see. This is the little band that we have some tools in our eyes to see. In terms of wavelength, these things are in the nanometers range. So typically these are on the hundreds. So a nanometer, as you can see here, these are roughly 3.8 times 10 to the minus 7 to 7.8 times 10 to the minus 7. That's really the band that we can see with our eyes. If we go to longer wavelengths, so we move over to the right, we hit this other sort of subcategory of the EM spectrum called infrared. Infrared, we also can sense, but we can't see it with the same machinery or tools. These proteins in our eyes and our retina aren't sensitive to those, but they are. We do have sensitivity, but we sense longer wavelength photons, longer than red, as heat. So infrared radiation, we don't see it, but we can feel it on our skin when something is warm. These are like heat lamps at at a restaurant. If we subdivide that, we keep moving to the right, we cross into this realm called microwaves. So microwaves are these interesting longer wavelength photons. We don't really have a good way to sense these in terms of we don't have built-in machinery like we do for infrared and for visible photons, but we do utilize these as humans. As we all know, we use these things called microwave ovens, and without going on a huge tangent, I'll give you some sense for how a microwave works. So a microwave is tuned to deliver a particular photon wavelength, so it's got an exact wavelength that corresponds to water molecules and what water molecules need to absorb to cause them to rotate really fast in solution. And that's the whole basis of how a microwave oven works. So a microwave is this box that's got this thing called a magnetron in the corner. That magnetron shoots out a bunch of microwave waves into your food dish that's sitting in the bottom, and typically there's some water in your food. That's why you typically don't want to put a chunk of ice in there, because the water can't rotate. So you send those wavelengths in to the water. The water absorbs exactly those wavelengths, exactly that energy of photon, and they spin around really fast inside of this solution. What do you think happens when you've got a bunch of water molecules spinning super fast next to other molecules like proteins and sugars and carbohydrates, all the things that make up your food? Well, they start to bounce into each other, and friction causes them to heat up, which is the basis of how a microwave oven works. It's also why if you've got an ice cube and you put it into a microwave here, in an ice cube, you still have water, but that water is not free to rotate. It's locked in a crystal that we call ice. And that's why microwaves aren't really good for thawing things, because they can't rotate these molecules. Those are restricted in the crystal form. Okay, so microwaves are longer wavelength. We have radio waves out here. We do have some machinery as humans. We can hear certain pressure waves that are of the frequency of radio waves, but typically we have to amplify these using these things called transistor radios. These are really long, so typically radio waves are subdivided into two categories. FM are a little bit shorter wavelength, and AM are really long wavelength. Sometimes AM waves can be on the order of a kilometer, which is huge, right? If we're thinking about visible light, we have machinery in our eyes to measure, and that's on 10 to the minus 7 meter range. A kilometer is roughly 10 to the third meter. So we're talking about 10 orders of magnitude between these huge, long, elongated waves out here. Okay, so that's the long wavelength side of the spectrum. We can jump over to the shorter wavelengths. So if we go from the violet side of what we can see, so around 380 nanometers, and we push that in the shorter wavelength direction, we go to the UV side. Some humans can see a little bit into the UV. Several animals can see in the UV. Most humans can't see much beyond 380. UV starts to be short enough wavelength, and we'll talk about this in a second, that the energy is high enough to actually start to cause damage to human flesh and tissue. And this is what can give rise to skin cancer. If we keep pushing towards shorter wavelength, we move into the realm of X-rays. So these are really, really short wavelengths, so they look like that, really, really oscillating fast. X-rays like this don't get absorbed very well by tissue and skin, and instead they bounce off of really dense objects like bone, which is why we use these to image our bones, because our sort of soft tissues don't absorb them well. And if we keep pushing further to gamma rays, these are really high frequency or short wavelengths, so they're just oscillating super, super, super fast. This stuff is pretty damaging to human tissue. It's also what's used in cancer therapeutics to kill tumors, because it will destroy cells pretty easily. And way out here, we don't have actually on this are cosmic waves or cosmic rays. And those are really, really short wavelength oscillating photons that come directly from the sun in little bursts. And so all of this is light. Light is not just the stuff we can see. Light is all of this. So this entire electromagnetic spectrum is light, because light is really just a photon, and the spectrum subdivides photons based on really how long or short its wavelength is, the wavelength being that distance between peaks and troughs. Okay, so it turns out that really most of what we know about molecules and chemistry comes from using different portions of the electromagnetic spectrum and using these photons and bouncing them off of chemicals and materials, and then observing what happens. And that whole field is called spectroscopy. So as I mentioned before, photons are sort of, they can be either particles or waves, and we'll talk about that a little bit in more detail. But when we're thinking about waves, they're these sinusoidal shapes, and as I alluded to, the top of the wave is considered the peak and the bottom is the trough, and any distance between peaks or troughs is considered this wavelength, which is the sort of basis of categorization in the electromagnetic spectrum. The frequency is also a really useful and directly related parameter to wavelength. And so the frequency is, if you were to have your sort of observation or your eyeball sitting right here, and this wave is moving in this direction, the frequency is how often the trough or the peak of the wave passes your line of sight per second. So frequency is number, or the units of frequency, the measure is typically in 1 over seconds, or per second, meaning how many times this passed you per second. So we also write this as seconds to the -1, those are equivalent. It turns out that seconds to the -1, or per second, is the same as the unit hertz, or Hz. So when people talk about, something's moving at 60 hertz, really what they mean is it's moving 60 times per second. So frequency and wavelength are intimately related by the speed at which light moves. And we all know that the speed of light is a fixed quantity. So the speed of light is 2.997 and a bunch of numbers times 10 to the 8 meters per second. We typically approximate this as 3.00 times 10 to the 8 meters per second. And so the wavelength of a photon, that Greek letter lambda, is going to be equal to the speed at which that light is moving. So this arrow here, how fast it's moving in front of you, divided by the frequency. And we're going to write frequency as this, we actually call it the Greek letter nu. It looks like a V, but it's got a little bit of a swiggle here on the right side of it. That's Greek letter nu. Or frequency. So let me just write this out. So wavelength, speed of light, that's a constant in vacuum, and this is the frequency of that light, which is, again, how fast or how frequent one part of the wave passes in front of the observer. In other words, we could write this as the frequency is going to be the speed at which that's moving divided by its wavelength, which makes sense. The speed at which it's moving divided by how far apart those troughs are. That's going to completely dictate how frequently you see the trough or the peak move in front of your eye. So these are good relationships for us to think about, because when we're thinking about the electromagnetic spectrum, as we did up above, you can see that the wavelength here that we talked about is running inverse to frequency. So as the wavelength got really long out here, the frequency got quite a bit smaller, which makes sense, because if you have long waves, then they're less frequently passing in front of you, the peaks or the troughs. Okay, so let's scroll back up here. This bottom figure just sort of helps us understand the relationship between wavelength and frequency in sort of a graphical way. And so these are just relating two different photons of different wavelength or frequency. And here you've got sort of a shorter wavelength, so a shorter distance between the peaks of the wave. And they're saying this is maybe 400 nanometer light, so we'd see this as violet. This is sort of the highest or higher frequency light that we can see. And if we double that, we just expand this wave and stretch it out to 800 nanometers, the frequency goes down quite a bit, and this becomes infrared radiation. So for example, if we had sort of this wave and this wave, and I asked you just generically which of these waves is probably bluer on the electromagnetic spectrum. When I talk about bluer, blue, remember, Roy G. Biv, violet being the shortest wavelength, so this is where wavelength is going down, red being longer wavelength as we get towards infrared. If I asked you this, you'd say, well, this is a shorter wavelength, so the wavelength is smaller here, which would mean this is a bluer type light, and this would be a redder type light, just relative to each other. It's also important to note that the amplitude, which is denoted here, that's the height of the wave from the centroid vertically, that has nothing to do with the wavelength or the frequency of the light. That's really just the brightness. So the brightness of light is the size of the amplitude, but the color or the frequency or the wavelength is completely dictated by the distance between the peaks and the troughs here.